Hello, let's work through the problems out of section 6.5. Graph the following function and show at least 2 cycles. In other words, two full periods. Okay, now the graph of a tangent function fundamentally looks like this. There's 1 full period of it. So 2 full periods is going to look like this. Okay. Now, the period of just plain old tan x is pi. So the period of tangent of omega times x, in contrast to sine or cosine, it's not 2 pi over omega. It's just pi over omega. Sine and cosine normally have a period of 2 pi. So if you're multiplying that argument by something, your period is 2 pi, the normal period, over what you're multiplying by. Since the period of tangent is normally just pi, the tangent of omega x is just pi over omega. So here we get the tangent of pi over 4 times x is pi over 4, which is just 4. What that tells me is that the width of each one of these periods is a width of 4. Okay, so overall, this whole graph has a width of 8. Now, typically, the graph of a standard single period of tangent, not multiplied by anything in here, just tan x, goes from minus pi over 2 to positive pi over 2. What we've done by multiplying that argument by pi over 4 is a horizontal compression. Okay, actually it's a stretching because pi over 4 is less than 1. So we've actually stretched this stuff away from x equals 0. We've done a horizontal stretch by multiplying that argument of x by a number less than 1. So we still want this first period to be symmetric across x equals 0, but its total width is 4. So that means this asymptote is going to be x equals -2, and this asymptote is going to be x equals 2. That's how I get a total width of 4 symmetric around x equals 0. If that width is 4, and this asymptote is x equals 2, then this one is x equals 6. Okay. Let's talk domain and range. So the domain is every number x that I can plug in, and that's going to be everything except the vertical asymptotes. Those are the only values of x that are not legit to be plugged into this function. So there are a few ways we can go about figuring out what that is. So just looking at the graph, the domain will be all x except 2, 6, 10, 14, if I keep adding on 4, but also if I subtract 4, -2, -6, -10, etc. Okay. We could also do this algebraically. The domain of our normal tan function is all x except pi over 2 plus or minus a multiple of pi. Okay. Now our function isn't just tangent of x, which means the domain of this would be all x except where pi over 4 times x is equal to pi over 2 plus or minus a multiple of pi. Specifically, the thing I'm taking a tangent of can't be one of these values. That's what we're saying here. The thing you take tangent of cannot be pi over 2 plus or minus a multiple of pi. So the thing I'm taking a tangent of in this problem isn't just x, it's pi over 4 times x. The thing I'm taking tangent of is not allowed to be pi over 2 plus or minus a multiple of pi. Now if I divide everything by pi, we get all x except 1/2 plus or minus k, and I need to be clear here, because I divided by pi, but I haven't accounted for that 4. So it's all x except those for which x over 4 is equal to this. Having divided out the pi, I now need to account for the 4, so I just multiply everything by 4, and over on the left, we'll get all x except 2 plus or minus 4 times an integer. All I've done is multiplied this 4 across. 4 over 2 is 2, plus or minus 4k. And those are the x's that are forbidden. This exactly matches what we found just by inspecting the graph. All x except 2, plus or minus 4 as many times as you want. Plus 4, plus 4, plus 4, or minus 4, minus 4, minus 4, etc. What about the range? Well, the range is all the y values that you can get out. But look at just one period of the tangent function. It has 2 vertical asymptotes, one going off to minus infinity and one going off to infinity, so it hits all values of y in between. The range of a full period of tangent is always all numbers. And since we're just doing more than one period, we're hitting all real numbers more than once. We're definitely achieving all real numbers in the range. All right, let's graph the following. 7 secant of x. Now, I just want to point out that this is 7 over the cosine of x. Okay. So, all we have to do is take the normal secant graph and then scale y values by a factor of 7. So let's turn our attention to just drawing secant of x, aka 1 over the cosine of x. So here is cosine x. There's 2 full periods of it. We'll actually go back this way as well. The highest value it ever gets is 1. And the lowest value it ever gets is minus 1. So what happens when I do 1 over that? Okay, I'll graph that in, say, blue. Here, cosine was equal to 1, so 1 over 1 is 1. Now as x moves slightly positive, cosine is getting smaller. It's decreasing. If cosine is getting smaller, 1 over cosine is getting bigger. As cosine gets very close to 0, secant has a vertical asymptote. If cosine is 0, secant's not defined. Similarly here, wherever cosine has a 0, we've got a vertical asymptote. So all of these places where cosine is 0 are vertical asymptotes of the secant function. But it doesn't just repeat that one picture I've drawn. So here to here, notice that cosine is negative, meaning 1 over cosine, or secant, is also negative. Here, cosine is negative 1. Where cosine is negative 1, 1 over cosine is also negative 1. So my secant curve also touches the cosine curve here. Wherever cosine is equal to plus or minus 1, secant will also be equal to plus or minus 1, because 1 over 1 is 1, and 1 over minus 1 is also minus 1. And then I just have to match these vertical asymptotes, keeping in mind positive versus negative. Since cosine is negative, secant is negative. Here, cosine is positive, so secant is positive. And now I'm repeating myself. Since cosine is negative, secant is negative. Here, since cosine is negative, secant is negative. Cosine is positive, so secant is positive, etc. Okay. A standard period of secant is from minus pi over 2 to 3 pi over 2. That's where we get one positive branch of secant and one negative branch of secant. Okay. Now in this function, in this problem, we don't just have secant, we have 7 secant. Well, that doesn't change a whole lot. It's just instead of coming down to a height of 1, when secant is equal to 1, this function will be equal to 7. So all I really have to do is come through, preserve 2 full periods of secant. So there they are, an up and a down and an up and a down. So that's 2 pictures that encompass everything. And instead of having their peaks and valleys at plus or minus 1, they're going to occur at 7 and negative 7. But we didn't change the frequency. We didn't change the period at all. So nothing much has happened there. Now I can answer again, what's the domain? It's all x except pi over 2 plus any multiple of pi, because that's where cosine is going to be 0 at pi over 2, plus pi, plus pi, plus pi, minus pi, and so forth. Where cosine is 0, secant is undefined. And the range, well, now the range is actually kind of interesting. Let me erase some of these marks here. What are the y values I get out? On this branch, I get out everything 7 and bigger. Here, I get everything negative 7 and smaller. Notice I can never get out anything between plus or minus 7. So the range can be all negative numbers up to and including negative 7. Also, everything from 7 and above, including 7. Negative infinity to minus 7 happens on these downward branches. Negative 7 and everything below. 7 and above happens on these upward branches. 7 and everything above it. But I never get anything in between, so everything in between plus or minus 7 is not in the range. You could also say the range is everything except y values from negative 7 to 7. That would be fine as well. Okay, graphing tangents, cotangents, secants, and cosecants is not especially commonly asked. It's worth taking a look at, but really focus on understanding sine and cosine and their graphs. Okay, from there you can get all the other functions. So definitely consider graphing tangents, secants, and so forth, but also definitely focus on understanding the graphs of sines and cosines first.